I need to finish. So 1919, there was a big breakthrough because they did an experiment to prove that Einstein was right. General relativity is right. So they did that very famous experiment that was led by Lord Eddington. So we'll talk about him later. So they did that experiment on 2 islands. So the Principe Island, which is west of Africa, and then in Brazil. So to understand the experiment, I just want to have a very quick review of physics, I guess, properties that has to do with the properties of light. So light wants to travel along a straight line. Okay, so for example, if you are looking at a bird in the sky, the light from the bird will travel along a straight line, taking with it the image of the bird, and then get to your eye, and then your brain see that bird. But if the air here, so this is the air, for example, above very hot sun, so it doesn't have the same temperature. So this is cooler air and this is hotter air. So the light coming from the same bird or from the sky, so let's say coming from the sky, right? So the image of the sky will still go along a straight line, but when it's going to go through a different medium, different temperature, the light will bend. So this is called refraction. That's how we have glasses, right? Because light bends when it goes from one medium to another medium. So light bend like this here goes to your eye, but your brain does not know about refraction. Your brain still think that the light comes along a straight line, so your brain thinks that the image it sees comes from here. So you're going to see what is called a virtual image. So you're going to see the sky on the ground. So this is called a mirage. And of course, you're going to think, oh, this is water. You know, I'm not going to die of frost. So you run, you jump, and there is no water there because it's a mirage. So you can see that, for example, when it gets very hot on the highway, the air here is very hot compared to there. So light from the sky will bend toward you, but your brain thinks that the image is on the ground. So you're going to see some kind of water, and there is no water there. Same thing here happen, but it's the opposite, right? So if it's the opposite, the light bend in the opposite direction. So if you have so this is very cool because it's close to the ocean. This is warmer air. So light coming from the boat, okay, carrying its image with it. Okay, so the light will bend, but your brain didn't take physics 101, so it thinks that the image of the boat is here and upside down. So you're going to see some kind of mirage, right? You see the boat upside down and above the ocean. Okay, so same idea when you have a star here. So this is the experiment that they did in 1990. So here you have the sun and here you have the earth. And of course, you cannot look at the sun because it will blind you. And there is, even if you look at it, if you look in this direction with a special goggles, you cannot see anything because there is not enough contrast because the sun is so bright. But in 1919, there was an eclipse. So the sun here was shielded. Okay, so because the moon was going in front of the sun, so they didn't have to worry about the sun being too bright. And here you had a star, and they knew the location of the star. And you can Google it, you know, I forgot the name of the star. So you were not supposed to see the star because the star, even though the sun was shielded, okay, do I'm recording or I still forgot? I did? Okay, thank you. So even though the sun was shielded, the star being behind the sun relative to you, you will not be able to see it. But because Einstein was right, and space-time is wrapped, right? Space is like a fabric and it's being wrapped because you have the sun here pushing on the fabric of space-time. So what will happen is that the light coming from the star start to go in a straight line, but then it goes down the deep here, okay, down the wrapped made by the sun, right? So light goes in this direction, but when you collect the light, okay, the telescope think that it comes from along a straight line, and you're gonna see the star here. So it's like seeing a mirage. So there is a shift between the apparent image of the star and the real image. Okay, and that was a revolution. That made Einstein from day to night a rock star. He became very famous. He was all over the news, and they show you a picture. You know, he was very friend. He was a close friend of Charlie Chaplin. So they were very famous at the time, and the people they were ready because it was after World War II. Okay, it was horrible. So they really wanted to think about something else. So people got very much into general relativity, and that's how Einstein became very famous because of this amazing experiment. Okay. How can I get out of here? I don't know what I'm doing. Okay. So this is called the eclipse, the solar eclipse that proved Einstein right. Island of Principe, and they also did it in Einstein in Brazil. I don't know what I did that I cannot get out of here. Okay, so again, it was an eclipse, so you didn't have to worry about the contrast, the brightness of the sun. The real location of the star was there, but light bent. Light bent because the sun was wrapping space-time, so that was the location, the apparent location of the star. So that was the proof that Einstein was right. Okay, it was a very simple, very elegant experiment, and it was led by Lord Eddington. So at the time, he was great. And then he's also the advisor of Chandrasekhar, and he's the one who ridiculed him when he came to England to be educated. So Chandrasekhar did a lot of work about white dwarf. So it's another story, but it's the same guy. So big breakthrough. 1919 general relativity, and Einstein became so famous. That was 10 years after special relativity. So it's fine. Newton still worked, right, as an approximation. So if you want to send spacecraft or satellites around the Earth, you are still going to use Newtonian physics. But if you want to study pulsars and black holes and neutron stars, very heavy stars, you need to use Einstein physics. Okay, so then 1920 we get to the expansion of the universe, so another big breakthrough. So when we think about the expansion of the universe, we think Edwin Hubble, because he takes all the credit for that, but there were other scientists, so it was not just only him doing the work, but it was also a very big breakthrough, because until then they thought that the universe was static, okay, not moving, or maybe because of gravity it will crash on its own. So they were not sure. And here in the 1920s, they were able to show, based on observation, that the universe is not static, it's expanding. But at the time, they thought it was expanding, but at a constant rate. Okay? And by computing for how long it was expanding, they were able to find the age of the universe, for how long it has been expanding, about 14 billion years. Okay, so To understand how he did it, let's review another physics principle, which is called the Doppler effect. Okay, and you'll always have so you have Doppler effect for sound, and you have Doppler effect, and it does it again. I don't know how to get out of here. So anyway, you have Doppler effect for light and Doppler effect for sound. So let's say you have someone on a bike. You have a biker, Harley Davidson. You know, it makes a lot of noise. If the bike passes by you, what do you expect? It's not going to do, no. It's not going to do, no. It's going to do, meow. Would you agree? Right? No. So what happens with the frequency? When it comes towards you, it's higher frequency than it is in reality. And then it moves away from you, it's lower frequency. Okay, so typical question, Doppler effect. No. Higher frequency, lower frequency. So it's like an apparent shift in frequency relative to the observer. So that, for example, here you have a noise making a noise, you know, from an ambulance. If it's coming, this is the reality, okay, of the source. If it's coming towards you, you're gonna hear a higher frequency. If it's coming toward you really fast, all those wave fronts will pile up and you have a shock wave that will hurt you. And if it's moving away from you, all the wave front move away from each other. That will be lower frequency, higher frequency, lower frequency. So it turns out, I don't know, I have an issue to go back here. You have the same thing for light. So you have a Doppler effect for light, and that's what you need to remember. There is something, I did something, but it's fine. So if light comes towards you, it's going to be higher frequency. So higher frequency is blue shift. Blue. So if you have the rainbow, right? So you have infrared, red, green, blue. Blue has a higher frequency, red has a lower frequency. Think of that frequency is energy. Blue is next to UV. UV, high energy. And then you have X-ray, even higher energy. Gamma ray, even higher energy. So blue has a higher energy than red. If you go to the other side, you have red, infrared, you know, safe, just warmth. And then you have microwave, and then you have radio wave. So anyway, when a source of light comes towards you, it's going to be blue shifted. But you are not going to perceive it unless it goes really fast. If a source of light moves away from you, it's going to be red shifted. So it's like if a galaxy like the Andromeda galaxy comes toward us, it's going to be blue shifted. Okay, what does it mean blue? Does it appear blue? I will tell you what it means, but I'm making it simple. And if a galaxy moves away from you, it's going to appear red. Okay, so typical question, red shifted away, blue shifted toward. Okay, so this is called the Doppler effect for light. It's another property of light you have for light and you have for sound. I did something to my computer, but I don't know what I did. Okay, we can watch this and make it faster because I'm late.
Stars are made up of a number of different elements. The sun is composed of about 73% hydrogen, 25% helium, 0.8% oxygen, and 0.36% carbon, plus smaller amounts of other elements. Each of these elements absorbs certain wavelengths of light. White light is made up of the full spectrum of wavelengths. But the presence of elements such as hydrogen and helium results in black lines in the spectrum. These are the spectral lines for hydrogen, and the black lines occur at the particular wavelengths that are absorbed by hydrogen. Here are the spectral lines for the Sun. By analysing these lines, scientists can tell what elements make up the Sun. And spectral lines can also be used to investigate what elements make up stars or distant galaxies. Scientists can also use spectral lines to work out whether a galaxy, like this, is moving towards the Earth or away from the Earth. Let's compare two sets of spectral lines for this galaxy as we expect them to appear. The positions of the spectral lines are based on the absorption lines for various elements as they have been measured in laboratories on Earth. If the galaxy was moving towards an observer on the Earth, the spectral lines would shift to the blue end of the spectrum. This is known as a blue shift. If the galaxy was moving away from an observer on the Earth, the spectral lines would shift to the red end of the spectrum. This is known as a redshift. The further the spectral lines are shifted, the faster the galaxy is moving away from the observer, and the further away the galaxy is from the Earth. Astronomers such as Edwin Hubble measured the spectral lines of hundreds of galaxies in the visible universe and found that most galaxies display a redshift. This led to the conclusion that the galaxies were moving away from the Earth and that the universe must be expanding.
Okay, so if I simplify, I will say that the galaxy get more red, okay, relative to us because they are moving away from us. So it will be red shifted. If a galaxy is moving toward us, it will be blue shifted. But that's really to simplify. In reality, what they are looking at the what we call the spectrum. Okay, so if you look at through a prism, and if you look at a galaxy, you're gonna see a rainbow. Okay, that's what you expect. Light goes through a prism, but on top of it, you see some kind of QR code. That QR code always has been used by chemists to tell what the elements, what are the elements you can find in a chemical, for example, or in a substance. So anyway, we'll talk about that later, but you have a QR code, okay? You look at a galaxy, you look at the sun, you look at a source of light, like fluorescent light here, through a prism, you're going to see a rainbow, if it's white light, and a QR code. If the source is moving toward us, the QR code is shifted to the blue. If the source is moving away from you, it's shifted to the red. So it's called the doppler effect for light. So it goes, okay, higher frequency, lower frequency. But that's how they were able to measure it. And you see, if you find the shift of the QR code, you can find the relative speed of the galaxy relative to us. Okay, so this is the physics in a nutshell. And again, so what did Hubble discover? He looked at the galaxies far away from us, and he was able to show that all those galaxies are moving away from us. They are all moving away from us, even though the expansion happens at a constant rate. So that was a very, very, very big breakthrough because Einstein didn't believe that. Einstein said, okay, the universe is static, and if it's static, it's because it's in equilibrium between two forces. One force that pulls all the galaxies together because it's gravity, and one force to pull them apart. So he introduced what it's called a lambda factor. He introduced a force pulling apart the galaxies just to explain why it was static, not moving. So if someone pull me this way, and if I don't want to move, someone else has to pull in the opposite direction. Okay, so Einstein had to recognize that for that he was wrong, that indeed the universe is not static, it's moving and it's expanding. So I can show you, I have this demo at home. Maybe I should turn off the light. So this is my 1D universe. You can see my 1D universe here. Okay, I made that universe. I am the goddess of that universe here. So you have cluster of galaxies, cluster of galaxy, cluster of galaxy. In between, you have a fabric. Okay, that will be the fabric of space-time that can be stretched. Okay, it can be stretched. And you see, the universe is expanding, but at a constant rate. If I'm located in this galaxy here, so if I'm located inside here, relative to me, I'm going to see the other one moving away from me, but this one will move faster than that one just because you have more fabric being stretched. Not because it's really moving faster, right? You see it's expanding at a constant rate, but just because from my perspective, that distance is going to increase, this distance is going to increase, just because space-time is a fabric. It's like a rubber band, right? So as you move farther and farther away, as you look farther and farther away, the relative speed will increase because I'm making more stuff, more stuff, more stuff, more stuff. Okay, so he was able to show that the universe is expanding at a constant rate, which I introduce the next concept here. If the universe is expanding, that means you can go back in time. It started just as a point. That was the Big Bang. Before the Big Bang, it was just infinitely small. And all of a sudden, you have like an expansion, exponential expansion. So remember, I don't know if it's in the test or final, but nothing can go faster than the speed of light except the universe itself. So during the Big Bang, it exploded faster than the speed of light. And all the light, do you see these little waves here that I made? This light that escaped from the Big Bang. Okay, finally, after the Big Bang, the universe was cooling down. This light was able to escape. This light gets stretched out. Do you see it got stretched out? So physicists predicted that if indeed the universe was expanding since the Big Bang, you should see like a background light in the background, part of space, time, part of the fabric that has been stretched out. So maybe it was in UV and now we expect it to be in microwave. You with me? Okay, so this is just a 1D universe. So we're gonna do 3D. It's actually 3D, but it's too hard to see that in 3D. So usually we do it in 2D. So if you have a 2D universe, okay, so if you have a 2D universe here, you can imagine you have a balloon. This is a 2D universe, 2 dimensions. You have all those clusters of galaxies, and you blow the balloon at a constant rate, But relative to you, all those other clusters are moving away from you, but this one is moving faster than this one because you're going to have more stuff, more fabric during the same time because it's like a rubber. As the balloon expands, and again, expanding at a constant rate, all these photons, so photons are corpuscle of light, all those little photons left over from the Big Bang expand with the universe. So if it was very hot, the universe to begin with, and it started to cool down, all those little photons, they can escape. Let's say they were in the UV, but because the universe was expanding, all of a sudden they will be in the microwave. Okay, that's gonna be. Scientists will find out about that microwave later, but it's based on the expansion of the universe. So that was 1920. I have a very nice video about Edwin Hubble, but I'm going to save it for later because I want to make sure to cover today enough for the test, which is on Wednesday. So here, same thing, there was a Big Bang, the universe, so this is 2D, universe was very hot, light could not escape, and then it expands at a constant rate relative to you, all the clusters. So they show galaxies. It's not really galaxies, it's like cluster of galaxies. Because inside our local group, for example, we are glued together and Andromeda is coming toward us. But if you look at other cluster or cluster of galaxies, they are moving away from each other. Now, in the 1990, there was a big breakthrough, and the universe is expanding, all right, but it's accelerating. So it's not expanding at a constant rate. Something make it, go bigger and bigger and bigger, faster and faster and faster. Which we call that dark energy. We do not understand. So dark matter is going to glue all the galaxies together in clusters, and then dark energy will move, like expand the fabric. So you have to understand that around you, you have stuff. You don't see it, you cannot touch it, but it's like rubbery, like jello, those horrible thing that the British they eat, like jello thing. Okay, except it can be expandable. Okay, and it's the space that pushes toward the Earth. Okay, so that was the Doppler effect. So there is I'm not going to show you the whole show, but there is a very famous episode in the Big Bang Theory, an excellent show, except it makes fun of physicists, which I don't like. But he explained that.
So what time does the costume parade start? The parade? Yeah, so the judges can give out prizes for best costume. The most frightening, most authentic, most accurate visualization of a scientific principle. Sorry, but there aren't going to be any parades or judges or prizes. This party is just going to suck. Thor and oh, Peter Pan. Actually, Penny, he's wrong. Peter Pan. I got a handful of pixie dust with your name on it. No, you don't. I hate what Sheldon's supposed to be. Oh, he's the doppler effect. Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
And this is exactly the definition. So he's not a scientist, right? I don't think he really understands what he's saying, but he was a very good actor. I mean, he's a very good actor, I guess. So it's a relative shift in frequency, okay, between the observer and the source. That's what the Doppler effect is. And you have the Doppler effect for sound, and you have the Doppler effect for light. So here, maybe I have a simulation. So you have your source, the source of light, and okay, so here nothing special. So this is the source of light, and it's going to be green. Now the source is going to move. So I'm going to move the source moving. So relative to you, if you are located here, the light, instead of being green, is going to be blue. Okay, this light coming toward you is going to be blue. If you are located here, the source is moving away from you, light will be red. So blue shifted toward you, red shifted away from you. And if it was possible to make it as fast as the speed of light, you're going to have a shock wave, right? Shock wave, because everything piled up. So if you have a sonic boom happens because all the source coming towards you, but so fast at the speed of sound, so all the wavefront will pile up. If you are located here, you have all this energy, and it's going to destroy your eardrum. Okay, any questions? I'm trying to make it in a nutshell. And I have a very nice movie, but I'm saving it for later. If I forget, remind me. So 1930s, another breakthrough. It was the beginning of radio astronomy. So you have a scientist. His name was, I don't know if I have a picture of him, Jansky. Jansky built the first radio telescope, but without knowingly. So that was not his idea. Okay, so let's see. Jansky radio telescope. Here, that was his radio telescope here. So he was not a physicist. He was an engineer, and he was working for Bell Laboratory. Bell Laboratory, amazing place. They were doing a lot of research at the time. It was an amazing place. Bell Laboratory came up also with the transistor, you know, the Silicon Valley, the Silicon Revolution that happened at Bell Laboratory also. So anyway, he was working for Bell Laboratory, and his idea was to detect noise coming from space, just noise from telecommunication, and that was interfering with long distance call. So he was not in astronomy. His goal was not to detect radio signal from space, because they didn't think at the time that you could collect radio signals from space or radio wave from space. He was just working for Bell Laboratory to try to get rid of this noise, the static noise, bzzz, that will go over long distance call. And then he detected a radio signal coming from the center of the galaxy. So without knowing it, he detected the signal coming from the supermassive black hole at the center of our galaxy that is sending radio waves. So he detected them, he collected them, but it took decades, like 10 years, until the 1970s, to understand that it was from a black hole. They understood that there was something mysterious at the center of our galaxy that was producing radio waves, and for the first time here it was detected. So that was in 1930s. So at that time, that was the beginning of radio astronomy. For the first time, they understood that not only you can collect visible light, okay, but you can also collect radio waves. And radio waves are great because they are not going to be stopped by dust or gas, right? They will go through the dust, through the gas. So this is how they took the first picture of a black hole, okay, using radio waves. But that was in, what did we say, 2017, something like this. The first picture of a black hole was taken using radio waves. So anyway, Jansky was the first one to build a radio telescope, even though it was not meant for astronomy, right? But he was the first one to come up with the design. So it was a very big breakthrough. So that was in the 1930s. So Carl Jansky. Is that clear? And then it's only in the 1970s that they've understood that it was coming from a black hole. So the center of our galaxy, remember the galaxy is like a flat disk. We live somewhere on the edge. You look toward the center here. That's where the black hole is, the center of our galaxy. And this, from our perspective, it's inside the Sagittarius constellation. Sagittarius, you can see Sagittarius from Florida, and better from the southern hemisphere, Sagittarius. And then they call the point Sagittarius A, that point, that specific point, where the black hole is. Okay. So I always forget when did they took a picture of our supermassive black hole 2022. Okay, and this is the picture 2022. It's done by a telescope called the Event Horizon Telescope. And this picture is done by collecting radio waves, not visible light, only radio waves. You can see the hole here. It's black because it's a black hole. Obviously. Any question? Okay, picking up on that, 1960, that's when they built this huge telescope, the Arecibo telescope in Puerto Rico. A lot of discoveries done thanks to this radio telescope. And I told you that it's broken since 2021 or 2020, and they didn't fix it because they found a new technology, right, to collect radio waves. What they do, they have smaller dishes connected to each other, and then everything happens like you have a huge dish, because this is very expensive, right, to maintain. So they stopped maintaining it, and they didn't fix it. But the idea is that you have radio waves coming from space, okay, parallel to each other, so all like along a straight line, and they will be reflected here at the focus, and that will be sent to a computer somewhere there and analyzed. Thanks to this radio telescope, they discovered the first exoplanets, ever. And those exoplanets were orbiting a pulsar. Okay, I told you already about that, but that was in 1993. Okay, so the first exoplanets ever discovered was detected by this telescope, right? And very surprisingly, so science about, always challenging the old ideas, right? You have to keep challenging. There is nothing written in stone if it's really science. And very surprisingly, those planets were orbiting a pulsar. So what's a pulsar? It's something very ugly, very dense. It's a corpse, a dead corpse. So it will be the leftover after a supermassive star died, exploded in a supernova, and what is left is called a neutron star. That neutron star, if it spins very quickly, it will behave like a lighthouse, and it's going to burp out X-rays, but also gamma rays. And then you can detect those radio waves. So what was surprising at the time is that those exoplanets were orbiting such ugly stars. So it could not be that the planets were around when the star was alive, because otherwise the explosion of the supernova will have killed them, destroyed them. So now they think that those planets, they were chilling out in space and were trapped by the neutron star. Okay, we already talked about that, but that's a pulsar, that's a neutron star. See, here you have a picture of a pulsar, and I'm stuck again. I don't know what I did. So anyway, the only thing you need to know, that was the first radio telescope built with the idea was to collect radio wave from space. They made many discoveries, so I invite you to dig into that, and including those exoplanets. It's one of the telescopes that was able to prove that gravitational waves must be a reality, because they were able to detect two neutron stars orbiting each other, but getting closer and closer to each other. So it means that they were losing energy, and they predicted that this energy loss should be into gravitational waves. Okay, so that means the fabric of space-time was shaking. But that came later, and there is another Nobel Prize for that. But you don't have to worry about that. I'm just reminding you this. So in 1995, there was this very famous movie. It's called Golden Eye. So it's part of the James Bond series. It was with, what's his name? Pierce Brosnan, very good movie, and they got the permission to film the movie at the Arecibo. So it was before AI. Because now we don't know what's real and not real, but we know that was in 1995, so it's real. They got the permission to make the movie at the Arecibo telescope. So it's a very famous scene, and of course a bad guy, and good guy, but it's okay. It's a good movie. So this is the Arecibo. It's a real one. They did for real. You see the dish? This is the tropical forest. I know she can have such a nice hairdo in the tropical forest and makeup too. Obviously, that will be the bad guy. Really bad guy. It's nice pull up too. So this is the focus here, you see? Well, you get the idea. Boom, bye bye. Okay, so it was very surprising that they got the permission to do that. He was a very good James Bond. And then let's see. So what you see here are two binary stars orbiting each other, but because they are shaking the fabric of space-time like two bowling balls on a trampoline, you see, energy is being lost as gravitational waves. So those two pulsars, the first two pulsars ever observed, was observed thanks to this Arecibo telescope. And then later, they were able to prove that, you see, this energy lost comes as gravitational waves, and they predicted it, and then they were able to prove it because they were able to detect gravitational waves. But that connect to the general relativity. Space time is some kind of fabric, a trampoline, and you see, when you shake that space time fabric, you make waves. So energy is lost as waves, and then they get close to each other, and then they can merge as a black hole, or they can merge as a new neutron star. You see, when they get close, really close to each other. So this is a white dwarf, and they are merging together because they are losing energy. Any questions? Okay, I still have this video I wanted to show you, but let's keep going. And then 1934, there was a genius. His name was Fritz Zwicky. He was working at Caltech, but he was like a very special character. Okay, he was not very nice. Remember how Newton was not a very nice person? Fritz Zwicky was not very friendly, especially to his colleagues. He knew he was a genius, okay? Obviously, he's a genius because he predicted dark matter based on observations. So he was observing a cluster of galaxies called the Coma cluster, and he was able to show that those galaxies inside the cluster, they are moving toward each other. They are moving relative to each other. So there must be a force. That force comes from gravity. But when he computed all the masses inside that cluster, he could not explain why do you have so much force. So it must be that there is something else. Gravity comes from stars. Gravity comes from black holes. Gravity comes from dust and gas. But it's not enough. It's not even enough. We have a missing mass. That missing mass is called dark matter. And he predicted it. Okay, you cannot explain otherwise why all the clusters are glued together in very large structure like Lanakia. So there is something, it's called dark matter. He predicted it. He was able to predict it. So he was a genius, but it was hard for him to be taken seriously because he was very famous. And I say it, please forgive me for the word. I say it, I'm going to say it just for the sake of the class. He was going around saying that his colleagues were spherical bastards. Why spherical? Spherical bastard. Because it doesn't matter which way you look at them, they are spherical all the way around. I found that very interesting. But of course, if you call your friends spherical bastards, they are not going to be your friend very, very long. So that's why his colleagues were very resistant to give him credit for whatever. So he did publish the paper. He did predicted dark matter. He also predicted pulsars. Okay, the guy was a genius. Pulsar and neutron stars, but they were not observed yet at the time. He predicted them and they were not observed. But because he had such a very unfriendly character, he had a hard time to make his idea recognized in the scientist community. So if you want to make friends, don't call them spherical bastard. That's not a good idea. I told you, connection okay, is everything. Unless you are a genius, so he didn't care, so then that will be fine. So he predicted dark matter and he predicted neutron stars. And he also was able to observe many supernovae. And he predicted that when you have a supernova, the remnant left behind could be a neutron star or it could be a black hole. Okay, so this is a very nice movie, and later on, okay, and that's a typical question on the final. 2004, they made this observation of what we call the bullet cluster. So if I ask you for the test, what is the proof of dark matter? It's the bullet cluster. Okay, and I'm going to show you a very nice video that explain why. That was before what's his name, Tyson, Neil deGrasse Tyson. He demoted Pluto in 2006, and he went a little bit off, in my opinion. But 2004, he was fine. In my opinion, okay, it's my opinion. You don't have to share my opinion. Everyone has an opinion.
You're watching a Nova Science Now video podcast.
Galaxies are purple. What color are yours? Mine are sky blue.
Here at Nova, we do a lot of things in the name of science.
Are you ready? Ready. 1, 2.
Just ask Nova Science Now host Neil deGrasse Tyson. And not all of it is done purely for fun. Like astronomer Doug Clow, sometimes we're trying to explore the deepest mysteries of the universe. And dark matter is definitely one of those mysteries.
When astronomers refer to dark matter, right, we mean something that doesn't interact with light in any way. It doesn't give off light. It doesn't absorb light.
Scientists like Cloud think dark matter makes up 20-some% of our universe. But there's something else they aren't so sure about.
We don't know what dark matter is. We think it's probably some sort of particle that we haven't discovered yet, but it might turn out to be something different. Not entirely sure.
So why is Cloud convinced that it actually exists? Say hello to the Bullet Cluster, two immense groups of galaxies billions of light years away that offer some clues to the dark matter mystery.
So the Bullet cluster is actually made up of two separate clusters of galaxies. About 100 million years ago, gravity had pulled them together and smashed them into each other. So in this collision, we have these two types of matter. We have the galaxies, and we have 100 million degree gas, which sits between all the galaxies. 100 million degree gas, yeah.
So what, you might be asking, do the galaxies and gas of the Bullet Cluster have to do with dark matter? Let's create a mini Bullet Cluster collision to demonstrate, and here to help is Neil deGrasse Tyson.
So when we take these two separate clusters of galaxies in the Bullet cluster and smash them together, the galaxies continue straight on without really any effect. The gas clouds, however, are going to behave just like any other sort of gas, and so they actually do collide. This is going to slow them down. And so now when we look at this cluster about 100 million years later, the galaxies are moving faster than the gas clouds, and so they're going to be further away from the center of this collision.
In the center of this collision are the intergalactic gas clouds, lagging behind the faster moving galaxies.
The galaxies are now in a physically separate part of the sky from what the gas is. And so we've separated out the two types of matter which we can see.
Now here's the important part. Matter creates gravity. More matter, more gravity.
90% of this matter is in the gas cloud, and so that is where the gravity should be.
But when all the data was put together, that wasn't the case.
Instead, we see that most of the gravity is actually around the galaxies. And that tells us that something else has to be there causing this gravity. It can't just be the stars and the galaxies themselves.
So is this evidence for dark matter? Let's ask three top experts in the field.
There is clearly some stuff there that is not normal matter, and that's making a lot of gravity.
I really believe that there is some drama today. So I think the bullet cluster really is the silver bullet, kills off a lot of theories trying to explain away dark matter.
Although the dark matter mystery isn't completely resolved, we may have good reason to be grateful for this mysterious stuff.
Dark matter is basically the glue that holds all the large structures in the universe together. So without dark matter, we would not currently be here.
So 3 cheers for dark matter, whatever it may be.
So it's a very nice video, okay? So this definitively test number one, I will go over it like maybe not at the beginning of the class, maybe mid-class and Monday, but it's going to be very easy. But anyway, dark matter exists, 25% of the universe, we don't know what it is, 75% is dark energy and we don't know what it is. And you have other clue for dark matter. So remember how I told you that light will refract, it will bend. Okay, so if from Earth here, you see, you are looking at this galaxy here very far away, and you have so much dark matter, so much glue that fabric of space-time is being wrapped. Okay, so light coming from this galaxy here, it's going to bend, it's going to be refracted, and we're going to think that the galaxy we are looking at is over there. So it's a virtual image, it's a mirage. So this is called gravitational lensing, and it has been observed, and here we go. It's another proof for dark matter, that glue, and we don't know what it is. And it works the same way, like if you have an what it's called, amplifier glass, magnifier glass. If you have a magnifier glass, you are looking at a bug. Here, light will bend as it goes through the glass, but your eye thinks it comes from along a straight line, and you're going to see a huge bug. But it's a virtual image. You try to catch it, and there is no thing. So it's called refraction. It's the same idea. Okay, so for test number 1, we still have this one to cover. I will do that Monday. Okay, it's about, let me introduce that. It's called the cosmic microwave background. So if you know that the universe is expanding, okay, so universe is expanding, yeah, like a fabric. And I already told you that after the Big Bang, just after the Big Bang, light was able to escape. Light was very hot, so high frequency in the UV. And now the universe was expanding, but light was part of the fabric of space-time. And you see, as the universe was expanding, light that escaped the Big Bang was also expanding. So it was stretched. So from UV, okay, it went to microwave. That was expected. And it was predicted by a scientist from Princeton University named George Gamow. He said if the universe was expanding since the Big Bang, we should see this light, okay, this background light after the Big Bang, just after the Big Bang, expand as well. And because they knew that the universe was expanding for 14 billion years, they were expecting to have this light in the microwave. So this is called the microwave background radiation, predicted by George Gamow from New Jersey. And he was setting the experiment. He was about to do the experiment, and there was 2 scientists, again from Bell Laboratory, engineers, and they were working with a huge radio telescope, a huge antenna, okay, and their goal had nothing to do with the physics, right, with the astronomy. Their goal was again to work on the static, the noise, and they collected the microwave background, and they got the Nobel Prize, and guess what? They didn't share the Nobel Prize. Isn't that terrible? He was the one who developed the theory, who said, who predicted we should see that background after the universe was born, and they didn't share the Nobel Prize. They because when you get the Nobel Prize, you can have no more than 3%. You can have 3% maximum. You have a huge amount of money, and then you have to share. So I guess that if you divide by 2, it's better than if you divide by 3. But that's the story. There was a very nice video that explained that, but I don't know if we have time. Let's see how long is the video. So first of all, I have to find it. No, I'm gonna show you this one because this one should not be too long.
Look at the night sky in any direction, past all the stars and more stars and galaxies and superclusters of galaxies, you will see light that has been traveling for 13.7 billion years to reach Earth. It's the oldest and most primeval light in the universe, a picture of our cosmos in its hot younger years, and it's called the cosmic background radiation. Of course, you can't really see this light with your naked eyes because it's in the microwave band of the electromagnetic spectrum, but it is visible to radios and radio telescopes, and even makes up a small portion of the salt and pepper on an analog TV. Where does this luminescent background come from? Well, just after the Big Bang, the entire universe was still so small it would have been very dense, scorchingly hot, and because it hadn't yet had time to get rough and uneven, it would also have been scrumptiously smooth. For a while, things would have been so sweltering that electrons didn't settle down as parts of atoms or molecules, but instead roamed freely in a kind of red-hot cosmic soup. That soup would have had lots of light bouncing around it too, scattering off of electrons and protons like a hall of mirrors. However, as the universe expanded, there was less and less energy to be had in any one place. And when things had cooled to just below the temperature of the sun, pairs of electrons and protons no longer had the energy to resist each other, and they fell into the electromagnetic embrace we call the hydrogen atom. These electrons were so enamored by their new proton love interests that they effectively began to ignore all the light bouncing around them. So with fewer free electrons for light to interact with, the universe suddenly became transparent, and all the pent-up light was sent forth in whatever direction it had been headed after its last scattering, doomed to travel alone and unnoticed through the cosmos. That is, until it bumps into something solid. When we finally see it here on Earth, this light has been stretched so much by the 13 billion year expansion of space that, like a record, slowly power. Its frequency and color have shifted from the original sunlight white all the way to cool microwaves. Thus, it's often called the cosmic microwave background radiation, or CMB. And just as we can tell the temperature of a red or white hot iron from its glow, this light tells us the temperature of empty space, currently around 2.725 Kelvin, or minus 270 degrees Celsius. However, the universe isn't exactly 2.725 Kelvin in every direction. If we look closely, there are small and seemingly random but noticeable bumps all over the place, kind of like milk that's starting to curdle. Our best understanding is that these cosmic curds formed as quantum fluctuations in the otherwise creamy infant universe, and then began to coagulate as the universe cooled and expanded. It's hard to overstate just how small or unbumpy these fluctuations of temperature and density were to begin with. The hot or cold spots were only hotter or colder than their surroundings by a factor of about 1 in 100,000. That's like noticing that a bacteria makes a beach ball bigger. But while this clumping of the universe initially resulted in small variations like the ones we see in the CMB, later on the chunky curds of primordial soup attracted each other gravitationally, and they ultimately coagulated and coalesced to form all of the massive structures in the universe that we see today, like planets, stars, galaxies, and superclusters of galaxies. So when we look up at the night sky past those galaxies and see the ancient light of the cosmic microwave background radiation, we're literally seeing the starting point, the proverbial cream, if you will, from which the starry curds of the universe congealed. Or quite simply, proof that the moon really is made of cheese. To give you a more complete experience of how awesome the cosmic background radiation is, we've made an adventure map showing it as if it were the out-of-this-world geography of your favorite fantasy series. Except it's really the first picture taken of our universe as a baby. We've included pictures of constellations and galaxies with the map, plus an overlay of what the sky looks like in infrared. And if you're feeling imperial, you can help name the oceans and mountains on our map. Head over to bigbangregistry.com to start exploring.
Okay, it's a very nice, it's a YouTube channel. It's called Physics, Minute Physics, something like this.
Past all the stuff.
So anyway, we'll finish on Monday. I'm almost done, and then I will give you some hints for the test. The test is super easy. Try not to miss it, because otherwise I don't have any time for makeup except during my other classes, so it could be disturbing. And so try not to miss the test, number one. And now it should be so we watch one video here next time, and Edwin Hubble as well. We're almost done, right? So universe 75% dark energy, dark matter 25%, and here we only know that about the universe, so not much.